108 for the department, and he defended his PhD in 2015. He did his PhD on robotics, and then he has been diverting to Linköping. But now Björn is back again. I'm very happy for this, and he's going to talk to you about modeling of cars, which you've been working on for many years now. Welcome.
Okay, thanks a lot for inviting me to give this guest lecture in this course. I'm very honored to participate in the course here. Yes, so the topic for today's lecture is automotive modeling. And I've decided to give this lecture the name, an overview of model components. Because I mean, going very deep into automotive modeling would require a complete course. So what I will try to aim here today is to give an overview of the kind of model components and what key characteristics there are when investigating and simulating and optimizing automotive systems. So I will start by giving an introduction to the subject. Then I will discuss a bit about propulsion and powertrain dynamics and how the vehicle is able to move forward. Then discuss braking systems and wheel dynamics. And then spend some slides on discussing the tire-road interaction modeling and the dynamics associated with that, because that turns out to be a key aspect in many of the system modeling properties of automotive systems. Then I will discuss steering and suspension dynamics and then integrate that into complete chassis dynamics models. Then I will also discuss a bit about experiments and model calibration. How can we actually determine the parameters that we need to be able to simulate based on such models that I will discuss during the lecture. And then I will conclude with a summary. And then I would already now like to advertise an upcoming lecture by Mattias Strandberg from Modelon. And it was intended for this first day, but due to some rescheduling, that lecture will happen on May 5th. And there he will discuss how one can do, for example, automotive modeling, but also other kind of modeling for other systems using a tool called Modelon Impact. And that's based on Modelica for describing the system dynamics. So I really recommend that as a follow-up to this lecture that is more theoretically oriented. So let's start with an introduction to this subject of automotive modeling. So there is quite a large community around vehicle modeling and vehicular systems modeling. And also the recent developments within self-driving cars have accelerated that development. I mean, we both need to extend the scope of the modeling and the types of systems that we need to be able to model. And also the need for advanced simulation of control systems integrated with vehicular dynamics is really important and has been even more emphasized by these developments. And I would also say that there is quite a large user groups for Modelica within automotive modeling. So the automotive industries, they were quite early on adopting Modelica and model-based engineering and modeling as a tool to use in their activities. And also I would say that vehicular systems, they lend themselves quite well to component-based differential algebraic equation system modeling. It's typically quite a few components with well-defined interfaces. And as I said in the beginning, this lecture aims to provide an overview of some model components that you will encounter when you set up models for this kind of systems. And also, I think that there are many opportunities for course projects in this course within this subject area. So if you are interested, I would be very happy to discuss projects that you can do for credits within this course as well. And those can, for example, be connected to the Modelon Impact and the Modelica-based tools that Mattias will talk about next week. Okay, so I mean, what key components of a vehicle do we typically have when we should do modeling? Yeah, so we have some kind of powertrain and some braking system that is typical for a vehicle. I mean, the powertrain system is to deliver the propulsion to the vehicle. And then we, of course, need some kind of braking system as well to be able to decrease the velocity of the vehicle. Then we have the important parts of the wheels and the tire dynamics. I mean, the interaction between the tires and the road surface is really important. I mean, that's what makes that the power that we get from the motor or engine is really able to accelerate the vehicle motion. And then we have steering and suspension dynamics so that we can have a comfortable ride. We also have the complete chassis dynamics that describe how the vehicle chassis and thereby the vehicle body is moving. And then something that I will not really cover in this lecture, but is nevertheless important, is driver modeling and also environment modeling. Because I mean, the vehicle is typically operated within some specified environment. So there is some interaction with such characteristics as temperature, the road surface, other characteristics that influence the different model components. And also, as for many other kinds of modeling, I mean, we need to start with the question, I mean, what is the purpose of the vehicle model? I mean, what should we really use this model for? What kind of fidelity do we require in terms of different modeling aspects? And there are quite a wide range of applications for vehicle models. And one obvious is simulation. And that could be as part of a vehicle design process to really determine the specification, the geometry of a specific vehicle. It could also be for validation, certain characteristics, certain features of a vehicle. It could also be in terms of control design. I mean, we would like to evaluate or develop some control functionality, and we need a model for that. And depending on the purpose here, the model could look very different, especially in terms of the complexity of the different modeling components. Then there is also a need for vehicle models in terms of dynamic optimization. And that is something that I've been working quite a lot with during the past, say, 10 years or so, using automotive models and vehicle models to really being able to decide, for example, optimal vehicle maneuvers, other kinds of optimal characteristics, optimal inputs to a vehicle model. And for example, if we should use the model for some dynamic optimization, we need to make certain considerations. It could be that we cannot use the same kind of model as we use typically for simulation, that when we are going to do optimization. So these kind of considerations we need to do when deciding on the modeling approach that we should use. So let's go into a bit more about the details of vehicle modeling. And here is an illustration from a book on vehicle dynamics of the car, and say that this is the system that we are going to model here. So we have a coordinate frame, we have 3 axes, we have the y-axis, x-axis, and the z-axis here. So the x-axis here, that's oriented towards the longitudinal direction of the car. And then we have the y-axis here, according to the lateral motion of the car. And then we have the vertical motion or vertical axis here along the z-axis. So in automotive modeling, we often call this the vehicle body. That is something that is supported by a frame that consists of the suspension system and other frames. And then we have the wheels, and the wheels are in contact with the road. And then we have some powertrain system that delivers power, makes the wheel rotate. And then we have the interaction between the wheel and the road that actually makes the vehicle accelerate forward. And then we also have rotational motions of this vehicle body. So we have the pitch motion along this y-axis. We have the roll action along this x-axis, And then we have the yaw here along the z-axis. So this is a complete 6-dimensional translational and rotational system that we need to model. And then in addition, we need to consider how the wheels behave and how they interact with the road. And we need to consider how the power or the torque actually to the wheels are delivered. So those are the kind of the subsystems that we need to consider in order to have a full vehicle model. So I will start with discussing the propulsion and the powertrain dynamics. And the definition of the drivetrain is that it includes all components that are required to deliver power to the driving wheels of the vehicle. So it does not include engine or motor, depending on the kind of power delivering unit that we have in the particular vehicle. And then we have the related concept of powertrain that includes both the drivetrain and the engine or motor. And the type of engine or motor that is in our car will, of course, influence the type of modeling that we need to do. I mean, we have the internal combustion engines powered by diesel, gasoline, or ethanol-based mixtures. That would require some modeling that is particular for those kind of systems. We have battery electric vehicles with an electric motor and a slightly different drivetrain based on that. We have hybrid vehicles that both contain internal combustion engines and electric motors. And we also have, for example, fuel cell electric vehicles powered by hydrogen. So, I mean, the type of powertrain system will influence what kind of modeling we need to do for this system. And for example, there are dedicated drive cycles or driving missions that are typically used for system and control design in this area. So that could be a specific driving mission that are, so to say, often standardized. I mean, this is a driving mission that we would like to use to evaluate how good our powertrain system is performing. So that is often used by many automotive manufacturers. So let's go a bit more into detail what we need to model in this kind of system. Yeah, as I said, I mean, we have the engine, the motor. Here it's illustrated with an engine that could go through a clutch. Then we have the transmission that contains the gear ratio. And then we have the propeller shaft that brings the power forward, so to say. Then we have the final drive here that contains the differential that, so to say, distributes the power to the respective wheel here. And then we have the drive shaft that actually brings the torque to the wheels where we would like to have the power to bring the vehicle forward. And here we can see that, okay, here are quite a few interacting components. So we start with the engine or motor, but at the end we would like to have the power at the wheels here. And this is for a car where the engine is mounted at the front of the vehicle, and then we have a rear wheel driven vehicle here. So what could be interesting here, and what often is a challenge in the modeling, is that, okay, because of these quite long shafts and also non-linear flexibilities in the clutch here, this could be a quite challenging system identification task to determine parameters and parameterize the different components that we need to establish a description of this system here. So essentially we can make diagrams of this type to describe the model. So we start here with engine with some torque. And there are, for example, friction effects involved that we need to consider. And then there is a series of so to say, transmissions and the transformations of this torque and corresponding rotational angles until we reach the wheel. So each of these blocks here, they will contain dynamics. And for example, it could be nonlinear flexibilities so that we can model using mass spring damper system, rotational mass spring damper systems. where we integrate, for example, nonlinear springs to model these nonlinear flexibilities. So in the end, we will get some force FL here, which is the resulting traction force. So I mean, we can go all the way from the engine to describe how our traction force or the force on the wheel is established. And then there is the area of aerodynamic and rolling resistance, which often is very important when simulating a vehicle model. So a low complexity model for aerodynamic resistance, or often called air drag, is given by this expression here. So the force that, so to say, opposes the vehicle motion because of the wind or air in general is given by this expression, that is a drag coefficient, the vehicle cross-sectional area, and then the air density and the squared velocity. So this is a force that increases with velocity as a square. And this is based on fluid dynamics, could be dated back to Lord Rayleigh and his results. And for practical vehicle dynamics and vehicle simulations, there are tabulated values for different vehicles, because that's an essential part when designing a vehicle. How much is this drag coefficient and the vehicle cross-sectional area, so that we can, in many cases, try to decrease the aerodynamic resistance.
There's a very large, a factor of 5 variation for a passenger car.
Yes, exactly.
What are where do you have the lowest value, where do you have the highest value? Do you have some examples of that?
Yeah, so if you go, for example, to racing cars, okay, where you have they have a low profile, and they try to minimize the aerodynamic resistance as much as possible. Whereas larger cars, I mean, having a large cross-sectional area, they tend to have very high value. But I agree, I mean, it's a very large span of this integrated coefficient and how much aerodynamic resistance you get. And I mean, there are much more complex dynamics for this aerodynamic resistance. And for example, racing cars and design of racing cars, you really need to investigate that kind of models in detail and have a detailed description of such dynamics. Then there is also a common model for the rolling resistance. And the rolling resistance is often described depending on the mass and the velocity here, and with some coefficient C1 and C2 that could be determined from experiments as well. And these coefficients, they're very much dependent on the tire properties. And if we then consider, I mean, what is affecting the vehicle motion or the vehicle propulsion? Yeah, so we also have a gravity force. So if we are driving on a road with a certain road angle, then we also will get the contribution from the gravity. And this we could describe, for example, using this expression here. So if we then, so to say, sum up the forces that are involved in the vehicle propulsion, we can get a first model here by using Newton's second law of motion, that m times the acceleration is the traction force delivered by the powertrain system. And then we have certain opposing forces. It's the wind aerodynamic resistance, we have the rolling resistance, and then we also have, if we are driving uphill, for example, that we will get the contribution from the gravity force. So, I mean, the detailed modeling is in computing these forces and have models for how we can compute these forces. But once we have the forces, we can rely on Newton's laws for establishing these relations here. Okay, so I will continue with discussing some aspects of the braking system and wheel dynamics. And yeah, brakes we typically have on our vehicles to reduce the speed of the vehicle. And it's often some kind of mechanical device that by help of friction is reducing the speed. And for vehicles, it's very common with disc brake or drum brakes, and that is the typical scenario that we need to model for this kind of systems. But also, if we have electric motors, we sometimes need to model regenerative braking. I mean, when we, so to say, use the electric motor to decrease the velocity of the vehicle as well. So, I mean, we somehow turn the vehicle or the motor into reverse speed and make it as a generator to convert the kinetic energy of the vehicle into something that we can either store in a battery or use directly in some other form of energy. So, I mean, this kind of regenerative braking is often something that needs to be modeled in terms of electric cars, battery electric cars. And also, if we should model a modern car, I mean, we need to consider all control systems that are involved in that kind of braking situations. And we have, for example, the anti-lock braking system that is standard in all passenger cars today. The idea is that we would like to maintain traction by avoiding wheel lock during braking. So, I mean, we don't want the wheel to lock when we are doing heavy braking. So, I mean, maybe when you have experienced in your car when you're driving and you get this pulsing motion from the braking pedal, that is typically when the ABS system is intervening. Because you don't want to apply such high braking pressure so that the wheel gets locked, because then you lose controllability, so to say. Then there are also more advanced control systems involved here. So we have the yaw control and development into electronic stability control that affects the yaw motion of the vehicle. So if we, for example, enters a curve with too high velocity, we would like these kind of systems to assist us to keep the vehicle on the track or on the road. So, I mean, adding corrective yaw moments by individual wheel braking and appropriate wheel braking, given the geometry and the dynamics of the car. And this is also something we need to model and integrate in our vehicle system model. And then for autonomous or semi-autonomous systems, we also need to consider different kind of emergency braking systems. They are sensor-based. They are based on the situational awareness that we have in modern cars, and they also need to be applied and modeled in our vehicle models. So there are quite a lot of modeling that needs to be done also relating to the braking system of a vehicle. But that's, of course, an integral part of having a complete vehicle model. Okay, so if we then continue with the wheel dynamics, yeah, we can see here in this illustration from a previous PhD thesis here at the department that, okay, we have the interaction point here with the ground. So we have some kind of lateral force on the wheel. We have some tractive force or longitudinal force, Fx. Then we also have a so-called camber angle here, which is the angle between this axis here and the actual orientation of the wheel. And then we have different torques, the rolling resistant and the overturning torque on the wheel here. And then we also see that we have a so-called slip angle. And that's a very important angle when we consider modeling of the wheel dynamics, because we can have the situation that the wheel is pointing in a certain direction, whereas the velocity of the wheel is along another direction. So we have something called slip, and we have a certain slip angle that defines the direction of this direction of the wheel travel or the velocity with respect to the orientation or the direction of the wheel itself. And that slip angle turns out to be very important when we should describe the wheel dynamics and also the interaction with the road. And I will come back to that in a few slides. So let's make a bit formal, more formal definitions of these kind of slips here. So we have the longitudinal slip ratio that we call here kappa. It's often also called lambda in the literature. Then we have the lateral slip angle that we saw on the previous slide. And if we introduce the wheel radius as Rw, we have the wheel angular velocity and also the corresponding longitudinal and lateral velocities of the wheel. We can make some formal definitions for the longitudinal and the lateral slip. So if we start with the longitudinal slip ratio, we define this as the ratio between Rw times omega minus V divided by V. So how should we then interpret this? Yeah, we can see that the faster we rotate the wheel in relation to the actual velocity of the wheel, the more slip we will have. So, I mean, ideally we would have quite low slip so that so to say, what we deliver in terms of power to rotate the wheel will be quite close to the velocity that we actually have of the wheel. So this is then a description of the longitudinal slip ratio. I mean, how much is the wheel spinning in relation to the actual velocity of the wheel? So this is a very important variable to control for vehicles. And then we also have the lateral slip angle. And if we, to start with, just exclude this part here, this can be defined by geometrical considerations. But it turns out that in practice, there is a certain time before the full slip angle develops. So that we can view this relation here as a kind of low pass filter with a time constant that is determined by this coefficient here. And this value here, sigma, is called the relaxation length. And that is something that is often used in vehicular or tire modeling or wheel modeling to define or describe that it takes a certain time before the slip angle develops. But in the foundation, the slip angle is defined as we see here in this figure. So it's a measure of how much the velocity vector deviates from the actual direction of the wheel. And then we also have the so-called body slip. And that is something that we measure at the vehicle center of mass. And it's essentially a relation between the lateral velocity and the longitudinal velocity. So, I mean, if we don't have any lateral velocity as well, then this slip, the body slip, will be zero. And the more we are moving along the lateral direction in relation to the longitudinal direction, the higher this body slip value will be. Okay, so before making a short break, I would like to also discuss tire road interaction models because it's very much related to the wheel modeling. And the tire is, as we know, a very important part of the wheel because that's where the contact between the wheel and the road surface is. And that is how we can allow accelerating and decelerating the vehicle. And there are two key components. We have the longitudinal and the lateral forces on the tire here. So we have the longitudinal force along the direction. I can go back to this. So we have the longitudinal force and we have the lateral force. And that is what we would like to model. And there is a vast plethora of models for this kind of modeling of this kind of dynamics. And I will not go into details. I will just describe a few that we have been working with and mention some others and that is also commonly used for simulation of this kind of systems. And before going into the kind of models that is often used, we can just note that, I mean, the tire dynamics, that depends on the tire itself. I mean, how has it been designed? How is the structure in the tire? How is what kind of material is it? I mean, there are a lot of details when it comes to the tire itself. But it's also the road surface, the interaction between the tire and the road. And also the temperature, the normal load on the wheel because of the car body. And also a lot of other factors, environment factors that affects. I mean, the tire pressure, for example, the surrounding pressure, and so on. So, I mean, making detailed tire dynamics modeling, that's a quite extensive process. And I also think it's good to call it tire-road interaction models, because it's not only the tire. We need to consider how the tire is interacting with the surroundings, like the road. So, okay, how does then this tire forces look like? Yeah, so here I have an example of how the longitudinal tire forces could look for different kind of road surfaces. So here we have the longitudinal slip here along this axis here. And here we have, so to say, an equivalent to a friction coefficient. So if we are on high here on this axis here, it means that we get, so to say, a corresponding high traction force or longitudinal force on the wheel. So if we start here for a dry road on asphalt, for example, I mean, we see here that we model the force as a function of slip. And here we have first comparably linear region. So for low slip values, we can say that we have a linear relationship between the slip and the resulting force. Then we have some kind of maximum here. So if we are designing a control system for a racing car, for example, it would be very good if we can always control so that we are using the maximum peak here. And then if we consider how this curve here for the tire force varies if we are considering other kinds of road surfaces, we see that, yeah, it's not only the height here, the maximum, the amplitude of the maximum peak, so to say, it's also the shape of the curve here that changes quite drastically. So especially if we come to low friction surfaces like snow and ice, we have completely different dynamics in terms of the tire road interaction. Especially here for ice, I mean, then we don't have this peak here. And that is because we have the interaction between the tire and ice. And it turns out that it's essentially the same for quite wide area of slips here. So we need to know both the tire itself and the road that it is interacting with to be able to model the tire forces. So if we consider the first part for low slip in the low slip region, we can start by making a linear model. So we can assume here that, okay, for low slips, there is a linear relationship between the slip, the longitudinal slip, and the corresponding longitudinal force. And then there is a coefficient, C kappa here, which is called the longitudinal tire stiffness. And then correspondingly for the lateral force, we can also set up a relation between the lateral slip angle and the lateral force. And experimental data tend to support that, okay, also the lateral force is linear in a certain region here. So that would be a first model of the slip. That, okay, we have a linear relationship between the slip quantities and the corresponding forces. And this coefficient C alpha is called the cornering stiffness. But okay, if we should capture the so to say remaining parts of this curve, then we need to have some kind of more extended model. And a model that has become very popular in terms of vehicular system simulations is the so-called magic formula that is proposed by Pacheco and the co-workers. And the origin for the name magic is that, okay, it's a kind of empirical model, or at least semi-empirical model that's surprisingly well, or not surprisingly, but it covers the experimental data in a very good way. So if we consider this combination here of trigonometric functions, the sine, arctangent, and plot this in a diagram here, we can see that we can capture exactly this peak here that we observed in the experimental data. So it's a matter of finding these parameters, the C, B, E, so that we can make a curve fit to experimental data, so that we can have a description of the model here and that represent the experimental data. And as I mentioned, this model was developed by Hans Pacheca from TU Delft. He has written a quite extensive book that is called Tire and Vehicle Dynamics, and it's available here in the library. It contains a lot of interesting information when it comes to tire dynamics. So both in terms of theory and also experiments and model parameters. So I can really recommend this book if you're interested in more details on tire dynamics. And he is also the co-founder of one of the major journals within this field, vehicle system dynamics. Okay, so I mean, now we have a description of the forces for pure longitudinal slip and pure lateral slip. But what if we are having a traction force? I mean, we are accelerating at the same time as we are turning, for example. So we are in a cornering situation, and at the same time we are accelerating. So I mean, we have a combination of both longitudinal and lateral slip. Yeah, so there are very many different models that aim to describe this situation of combined longitudinal and lateral forces on the tire. I will just describe two of them here in this lecture. And the first is the quite common friction ellipse. That is based on the assumption that the longitudinal force and the lateral force, they are, so to say, on a certain ellipse. So if we, so to say, express the lateral force as function of the longitudinal force based on this ellipse expression, we can get the relation like this. So that is an assumption, and we will have a look at plots later on how that could look like in practice. But essentially, it gives a description of how the longitudinal force interacts with the lateral force. But there are also more elaborate models, and in the spirit of the Pacheca's magic formula, he has also proposed to use weighting functions to describe this situation when we have both longitudinal and lateral force. So he proposed to use this relation here with, so to say, the force, longitudinal force that we get from the magic formula. And then we use a so-called weighting function that is defined by this expression here, which in turn is dependent on this description here. So it's in the same spirit of the magic formula that we have a combination of trigonometric functions that can describe the relation between the longitudinal and lateral force. And then we can have a corresponding weighting of the lateral force Fy here.
Question.
Yes.
Is there any geometric motivation behind those geometric?
Yeah, so I think if we look at this plot here, that's a kind of consideration why this could be a reasonable model. So I hope that will answer your question, but we can come back to it after I've explained the plot here, but that's a good question. So, I mean, if we look here, this is 1/4 of the ellipse here. And I mean, the assumption behind it is that, okay, we cannot have full lateral force and longitudinal force at the same time. So there is a certain, the resultant force that we can get out from the tire that is limited. And that limit is described here by this friction ellipse. So that's the kind of motivation behind using this kind of modeling. I mean, we cannot develop more forces than what is, so to say, prescribed by the friction ellipse here. And then, okay, is there a need then for more advanced models? Yeah, what one can see in measurements of tire forces is that there are some more advanced dynamics that happen, for example, here for low lateral forces, that it is not exactly a friction ellipse. And that's why, for example, the weighting functions, they have been proposed to try to capture these observations from experiments. these weighting functions, they are more dependent on observations from experimental data. I mean, this is how typical tires behave when you put them in a measurement tire rig and measure. Yes.
When you simulate such a vehicle, you use a particular kind of the tire model perhaps, but then people that drive this vehicle, they go and buy cheap tires or expensive tires. How much does it vary between different tires?
I would say it varies quite a lot. And I think that automotive companies that do this kind of simulations, I think they need to apply some kind of robust design in the simulations.
They assume you buy shitty tires.
Yeah, exactly. I mean, we need to so to say make it robust so the vehicle functions, they still perform well if we have different kind of tires and the tires are worn, for example. Absolutely. So I mean, this is something we need to consider when we model combined longitudinal and lateral forces. And we can then illustrate the resulting tire forces using this kind of surfaces here. So here is a tire force surface where we have the slip angle and the longitudinal slip. And then we have here on the z-axis the resulting tire force. So we can see that for different combinations of slip, we get different resulting tire forces from the wheel or from the tire. So if we consider here, if we make a cut here along alpha equal to 0, then that will correspond to the plot that we saw some slides ago for the longitudinal slip in relation to the resulting tire force. So if we imagine that we make a cut here at alpha equal to 0, that will, so to say, correspond to this peak here. So, but the interesting part is then also, I mean, what happens when we have combined slips? Yeah, and we can see that the resulting forces, they are varying quite a lot. I mean, it's not a flat surface typically. And for example, if we have high combinations of lateral and longitudinal slip, I mean, the force tends to decrease quite significantly. But I mean, that is only for one type of tire in connection with a certain road surface. And I mean, in a paper from 2013, we investigated different kinds of tires in relation to different kinds of roads. And the characteristics here could be quite different depending on what kind of tire it is and how you parameterize your vehicle model. And I mean, we can, for example, since we use these kind of models for optimization, it is quite important how this surface looks like if you should utilize the maximum possible of the tire forces. Because I mean, we would like to, so to say, maximize the tire utilization by being close to the peaks here. And just before the break, I would like to mention that in this kind of tire force diagrams, it's also possible to draw the resulting trajectories or the resulting traces of the tire force utilization during a vehicle maneuver. That will give an indication of how much of the tire forces that have been used when you, so to say, perform this particular maneuver. And here I have an example from one of our papers where we have compared the maneuver for dry asphalt compared to smooth ice. And we can see that this difference in tire force behavior on smooth ice is reflected in the tire force surfaces here. I mean, here we have the dry asphalt with this kind of characteristic peaks. But for the smooth ice model, it's quite different compared to how the tire behaves on asphalt. And we can also, I mean, there have been proposed how you can scale these kind of tire models to represent different surfaces. It's typically based on that you make measurements of the tire forces and then establish models based on that. And as we found when we worked with this kind of models for optimization is that, okay, models that have been used with great success in simulation, they're not always suitable for optimization, because the optimizer tends to, find the so to say limiting regions or limiting state space parts of the model, so that we, so to say, find loopholes in the models that we don't really see when we do simulations, because then we are typically in other parts of the model region. And as we know from Carl Johan's previous lecture on friction, friction is a complex phenomenon. And there have been proposed a lot of different models for tire force in tire road interaction models. And I'm just mentioning a few here. And these are, so to say, also based on that it's quasi-static considerations. The forces are functions of the slip or other related quantities. But they have also been proposed to use more transient friction-based models like the Lugre and also the Swift model that has been proposed by Pacheco and co-workers. So, this with tire modeling is an extensive research area, and depending on the fidelity of the model that we need, there will be differences in how we can apply this. Okay, with that, I suggest that we take a break and then we resume at 11:15. Most welcome back to the second part of this lecture on automotive modeling. So we have some topics left here, and I will start with discussing steering and suspension dynamics that will then lead us to more complete fuzzy dynamics models. So just some key concepts that often turns up in connection with steering dynamics, and that is the so-called steering ratio. And that is the ratio between if we turn the steering wheel and how much the actual wheels will turn. So there is such a ratio, and it's typically not 1-to-1. It's rather in the range of 10 to 20 to 1. So we would like to have much higher, so to say, granularity in terms of how much we can turn the wheels. And then we also, as we saw on the previous slide, we have the camber angle here, and that is the angle between the vertical axis of the wheel and the vertical axis of the vehicle with the perspective from the front. So sometimes we see on for example racing cars that we have a camber angle that is quite different from zero. And that's the reason why we have such a design in such systems, is that it will affect the handling dynamics of the car. So how we direct the forces and when we control the wheel angle and what happens with the tire forces in relation to the motion of the vehicle. Then there is also a common concept that is called the Ackermann steering geometry. So if we consider this kind of steering kinematics here, we can recognize that, okay, the left wheel on the axle and the right wheel on the axle, they will not travel along circular arcs with the same radii. So they will have different radius, and that implies that we should not have exactly the same angle for the right and the left wheel on the axle. And that was the mechanism developed already in the 1800s here. And it was at that time for horse carriages. But it's still used as a basis for the design of the steering kinematics for cars. Because if we would have the same steering angle, it would lead to that one of the wheels, they will have to slip all the time. But now we need to, so to say, compensate that by this mechanical device here, or mechanical construction. So that's a quite interesting invention that is used still in the design of the steering mechanism for a car. And even though it's a kind of quasi-static consideration how we should orient the wheels, it has clear implications on the vehicle dynamics as such. So there are a lot of discussions and investigations on exactly how this mechanism should affect the turning of the respective wheel here on the axle. Okay, so two more concepts that often turn up when discussing and writing about suspension dynamics, and that is the unsprung and the sprung mass. And the unsprung mass, that's essentially the wheels and the suspension system. And then we have the sprung mass, and that is, so to say, the remaining part of the vehicle that is carried by the suspension system, what we can call the vehicle body. So the unsprung and the sprung mass, that's typically something that turns up when discussing this kind of suspension and quasi dynamics modeling. And if we should consider a very first linear model for a four-wheel vehicle, that would be that we introduce some kind of inertia spring damper system in rotational coordinates to, so to say, be an equivalent of the suspension system and the effects of the suspension system along both the roll and the pitch directions. So for example, we can model that the moment that is produced by the suspension system in the roll direction is given by an expression similar to this, that we have some kind of stiffness that depends on the roll angle, and then we have a corresponding damping term that depends on the roll velocity. And then correspondingly in the pitch direction of the car, we can also have corresponding parameters that describe both the stiffness and the damping along the pitch direction, depending on the pitch angle and the pitch velocity. And all of these K and D are parameters that we need to determine to have a description of how the suspension system works. And the suspension system implies that we have a load transfer when accelerating or decelerating or even cornering with the vehicle. So it means that we will have time varying normal forces. And if we are using a differential algebraic equation based modeling approach, it's quite convenient because then we can, so to say, introduce this kind of differential algebraic equations that tells, the sum of the normal forces need to equal the total gravity on the vehicle. But there will be time-dependent changes, time-varying changes in how much normal force or no normal load that is on the respective wheel. And for example, for the longitudinal load transfer in the pitch direction, we can use the expression that we introduced on the previous slide with the stiffness and the damper to, so to say, make a relation here between how the normal forces will, they need to satisfy both this expression and this expression here. So we, so to say, connect our suspension dynamics modeling with how the normal forces will vary. And LF and LR, they are the front and rear distances from the wheel axle to the center of mass of the vehicle. So they are, so to say, geometric properties that we can measure on the car. And then correspondingly for the lateral load transfer in the roll direction, we can put up these kind of equations here, where we have the normal forces for the different wheels of the vehicle and introduce these as equations in our vehicle model. And W here is the half of the vehicle track width. So that's the distance between the wheels on the axle. And a very common model when it comes to investigation of suspension dynamics and also design of active damping, for example, in vehicles is the so-called quarter model. And that is illustrated here. And if we start from the ground, we have the tire, which is approximated with a spring damper system, according to this here. Then we have an equivalent of the wheel mass, and then we have a description of the suspension dynamics, or suspension dynamics with the spring here and the damper here. And then we have a quarter of the vehicle mass. So essentially, we represent the suspension system and its interaction with the tire dynamics and the wheel dynamics according to this expression here. So I mean, here the primary objective is not to describe how the tire interacts with the road, but rather how the wheel and the tire interact, how they interact with the suspension system and the normal forces of the vehicle. So this is a very common model for investigation of suspension dynamics. Okay, so now we will, so to say, use this suspension dynamics concepts and integrate that into more complete quasi dynamics models. And as a basis, we can say that, I mean, the model equations for the quasi dynamics is derived from I mean, analytical mechanics. So yeah, I mean, you are familiar with the concepts of Newton-Euler modeling or Euler-Lagrange modeling, and that we can use to establish differential algebraic equation systems for the complete quasi motion. I mean, I would say that, I mean, the principles are straightforward, but we should note that it's often a quite time-consuming process, and I would say sometimes a slightly tedious process to get all these equations in place, because it involves, typically, if you do a Newton-Euler approach, that you need to establish free body diagrams, you need to compute force and torque equilibria and so on to determine these forces. However, I mean, tools for symbolic manipulation could be very beneficial in this kind of modeling situations. And not least, I mean, there are extensive libraries in many modeling and programming languages available for that already, so to say, have derived these equations. And yeah, I mean, there are varying models of different complexity depending on what kind of fidelity we need here. And here we have two examples. So this is the so-called single track model. And here we have lumped the two wheels on each axle. So we consider this as the rear wheel, and this is the front wheel, that where we can control the steering angle delta here. And this is a model that is often used if we are, for example, investigating aspects related to the yaw dynamics of the car, or we are particularly interested in, I mean, the orientation of the car, and also having a model for how the different wheels interact with the ground. But if we then need more advanced models and we need to consider all four wheels, then we have what is often called a double track model. And here we have the individual wheels, we have the center of mass, and we have all the related variables for the rotational motion as well. So, I mean, this kind of double track models, they will include both roll and pitch dynamics and the associated load transfer in terms of the normal forces. And for example, we can consider the steering angle, so how much we change the orientation of the front wheels here, and the torques that we apply on the respective wheel here as the inputs to this model. So, I mean, that's essentially what, so to say, drives the fuzzy model here. I mean, we have torques on the wheels, and we can also control the delta angles here. So I will just give some examples of how the equations could look like. I mean, they tend to expand, especially when we increase the dimensions of the degrees of freedom and what we model on the car. But for example, I mean, the single track model for this kind of model vehicle representation here, they look like this. So, I mean, we have the velocities. We can use Newton-Euler to set up the forces that are delivered by the tire forces or the wheels. And then we can get this kind of differential algebraic equations here that relate how the acceleration along the x longitudinal direction relates to, for example, the yaw rate here and the forces that we apply on the wheels. And essentially we get this kind of, we have the X longitudinal, the lateral, and then we have the yaw direction here. So this is we can establish based on the Newton-Euler approach and identify in which directions the forces and moments act here. And then we also need to introduce the inertias here that describe how we can control the yaw, or how the yaw is evolving. And for example, in such a model, we can use the longitudinal tire forces directly as input and the steering angle delta. But we can also extend such a model with having wheel dynamics where we include the wheel torque as input. That, so to say, then results and generates the longitudinal tire force. And the equations for a double track vehicle model is more extensive. I just included them here to so to say give an impression of, I mean, what kind of relations is it? And I mean, then if you do vehicle simulations in Modelica, I mean, you will find these kind of models under the hood, so to say, because I mean it is based on relations between the forces and the derivatives of the states. So I mean, we can see some common patterns here with a single track model, but now we are considering the full 6D motion of the vehicle chassis. So I mean, we have both roll and pitch motion, and we are also moving in the yaw direction. So I mean, all of these variables related to the yaw, the roll, and the pitch, they will turn up in these expressions, because I mean the forces will change direction when the whole vehicle chassis is changing here. But I mean the global forces that, so to say, is provided by the forces from the tires, they are, I mean, still, I mean, derived based on Newton-Euler approach. I mean, we can decide the forces that we get from the different tires and how that, so to say, is influencing the relations here with the different variables. And just as an example, I mean, we can also derive the yaw dynamics according to this expression here, where we then need to establish the global moment on the vehicle as well. And if we, for example, consider the pitch dynamic motion, we can see that, okay, here the modeling that we have adopted for the suspension system, that will turn up in these equations as well. So the suspension dynamics modeling, I mean, that will affect the chassis dynamics motion. Yes, and then we have a corresponding expression for the roll motion, and similarly, the suspension dynamics will turn up here, because the forces that are applied by the suspension dynamics on the vehicle chassis frame, I mean, that will also be included in the model, and that is something we need to consider in the model as well. And then we can, of course, extend this kind of modeling to even more complex vehicle setups. And here I've chosen an example. It was developed in a previous PhD thesis by Magnus Jävert in collaboration with Olof Lindgärde here. And then this is a technical report where this model is described in detail, but it's essentially a 9 degree of freedom model for a tractor semi-trailer combination. So that is, we have the tractor here, and then we have the trailer that is attached to the tractor here with some connection here. And here we see that, okay, now we have 2 moving bodies that are connected with certain dynamics in the interaction point here. And this is also kind of systems that we would like to be able to model using the same kind of modeling principles and tools as we use for a passenger car. I mean, the same principles apply, but the equations, they tend to become even more extensive since we have more degrees of freedoms, more involved variables. So here it's really beneficial with computer manipulation when it comes to symbolic manipulation for this kind of vehicle models. And I mean, just to give some kind of impression for what kind of equation system and coordinate frames that are involved, this is the free body diagram that Magnus and Olof used here to describe this model and derive this model. So, I mean, we have the tractor here. We divide it into sub-parts so that we can establish the free body diagram. And then we need to establish the connections between the forces and the moments in the different coordinate frames here to, at the end, being able to get the model that describes the motion of this system here. So, I mean, especially for this kind of systems, it's very beneficial to use available tools for simulation, because, I mean, there we have a foundation that we can build on and use. But, I mean, at the end of the day, under the hood, it will be these kind of equations. I mean, it will be based on Newton-Euler equations that we get. Okay, so the next to final part, I will just say something about experiments and model calibration. And when it comes to the powertrain models and powertrain dynamics, that is often identified based on experiments where you drive with a vehicle on different roads with different slopes and different heights, so that you excite different parts of the powertrain dynamics. So that we can identify, for example, the flexible modes in the shafts and the clutch and so on to determine these kind of models. So it could be, for example, measuring the engine or motor speed and torque, the wheel and transmission speed, and do some kind of gray box identification for determining the parameters that we need in the models. And then when it comes to tire force measurements, there are dedicated test rigs, typically equipped with quite a few strain gauge sensors, so that you can actually measure the forces both along the longitudinal and the lateral directions, at the same time as you can measure the slip and in which direction you have the forces. And then for excitation and modeling of the vehicle dynamics, the chassis dynamics, there are certain vehicle maneuvers, certain predefined steering angle inputs, for example, that generate different kind of maneuvers. And one famous such is the double lane change. It's even defined in an ISO standard how that should be performed. And that is to really test the limits of the vehicle dynamics. And for example, investigating such things as the risk of rollover, for example. And also there are other, like the fish hook or the slalom maneuvers that could be used to excite the vehicle dynamics, and then record data and use that as a basis for the control and modeling. And this is an example of a double lane change maneuver that we have investigated in our research. I mean, the setup here could be that there is a suddenly appearing obstacle here on the road, and we need to do a very rapid and sudden change in the lane from the ordinary driving lane to the other driving lane with opposing traffic or oncoming traffic, and then as soon as possible get back again. But this is a very common maneuver to really excite the limits of the vehicle dynamics. And how this could look like in practice is that here in the left figure, I've included this tire rig measurement setup that was used in Jakob Sundenius' thesis here at the department some years ago. And then they were in Arjeplog in the north of Sweden with this mobile tire rig measurement setup. And then they, so to say, attached the tires here and performed measurements on this kind of well-defined surfaces that are available at this test sites in that region. But also in Linköping, we have this kind of cars equipped with different kinds of sensors. It could be IMUs, it could be this kind of laser sensors that measure the distance to the ground. That could be attached both here at the front and at the sides of the vehicle to determine inputs and experimental data that we can use as a basis for our modeling. So, I mean, at the end, we really need to do some kind of system identification to determine the actual parameters of our models. And this is how it could look like for tire force measurements and vehicle dynamics measurements. Okay, so then we have reached the summary of this lecture. And yeah, as a concluding observation, I mean, automotive modeling covers many different model areas. So it's everything from the powertrain to the chassis dynamics. And differential algebraic equation systems, they are a natural modeling approach to describe these systems, because there will be many different parts of a model that needs to be integrated together with each other to constitute the complete model of our vehicular system. And Modelica offers a language for such model descriptions. So with associated tools to Modelica, we can both simulate and optimize different vehicle models of different fidelity. And then, yeah, I would like just to mention again that next week, Matthias Strandberg from Modelon will come and describe and discuss how this kind of automotive modeling can be done in their tool Modelon Impact. So that will be an overview of what libraries are available and how can they be used to do this kind of vehicle model simulations. Okay, so with that, yeah, I have some additional references that will be available in the slides as well. But with that, I open up for questions or comments.
But first we give you an applause.
Thanks a lot. Yes.
All in all, a very general question maybe. All in all, the field seems very much developed. Like the models are, we know which kind of models work and we know which shape they have and we know how to study them. What are the biggest challenges research-wise that are still there?
Yeah, no, I mean, as you say, I mean, the automotive industry, they've used this kind of modeling approaches and built up a whole community around it. But for example, I would say that now with modern cars, autonomous, semi-autonomous cars, we have quite advanced sensor systems that need to be simulated as well. So it's also about not the vehicle itself, but everything that goes on around it and making sure and validating functionality of such systems, including sensor systems and the situational awareness about the environments. So I mean, I would say that there are, yeah, research and development challenges.
More on the higher level.
Exactly.
Which sort of interfaces do you think are there between this higher level of control? I mean, I would say maybe autonomy using a buzzword and these lower levels of modeling.
Yeah, I mean, depending on what kind of, I mean, requirements we have on the high level modeling, I mean, it might not be necessary to have the full detailed level on the, say, the tire dynamics or the powertrain dynamics. So, I mean, it relates a bit back to one of my first slides. I mean, what is the purpose of the model and what do we really need to, or what do we want the model to provide characteristic information about? So, I mean, I think that's yeah, a good first step to investigate and put up some requirements on the model and what approximations can we make, and what is the important part of the vehicle modeling, so to say. Yeah, thank you.
Yeah,
Yes.
a little bit of a follow-up question on this. So I was actually thinking about what you said with you have a lot of sensors in the car,
Yeah.
a ton. So
Yes.
and we talked about subsystems here today, like different models for different subsystems.
Yeah.
But how can you incorporate all the sensor data to actually improve your models further? For instance, I assume that your brake system can be improved substantially by utilizing sensor information on the like tire road interactions,
Yeah.
etc. Is that something that's investigated, or?
I mean, yes, I would say so. I mean, putting up, I mean, using advanced sensor fusion to determine different quantities and variables of, for example, the tire road interaction, and using, I mean, sensors to that purpose, and also using the available situational awareness information. So, I mean, I would say that that's definitely very interesting research and development problems that people are working with right now to, I mean, utilize the available sensors and computational power in modern cars to do as much and best as we can with that information. And that is not only for the, so to say, high level decision making, but also, so to say, propagating that information to the low level control systems for emergency braking, improving the electronic stability control systems, and making, so to say, a new generation of those kind of control systems. Absolutely.
So a follow-up question again. So
Yes.
how much of this, so a lot of this seems to be offline based computations. Like you have some models, etc.
Yeah.
Is any of this used online, like in the car whilst you're driving? What type of models do you actually have?
Yeah, I mean, now I didn't discuss that a lot, discuss that a lot during the lecture here, but I mean, code generation for real-time execution, for example, is one very important area for vehicular modeling as well. I mean, you use these the outputs from these model in the online control, both, I mean, for example, in supervision functions. I mean, is the car behaving in a good, in an expected way during this kind of maneuvering? Also, I mean, there are certain, so to say, trigger events for the control systems, the safety systems like the ABS system. We need to use sensor data and combine that with models to determine, I mean, when should we activate different kind of control systems.
Can you say something about racing and mathematical models? Are they used in connection with racing or?
Yeah, so I mean, I think that many professional racing companies, I mean, they are using mathematical models for their cars to try to both optimize the mechanical design of the vehicle and the chassis and everything that, and also as a way to perform as good as possible. So my impression is that they also have a high interest in this kind of vehicle model and simulations. Yes.
Since, as I understand, you have worked quite closely with industry.
Yeah, we have had collaborations. Yeah.
What is your feeling about the gap between research and industry? Because in some fields you see that industry is way ahead of research, and some other fields you see the other way around. That research proposes a lot and industry doesn't apply because maybe economic trade-off is not seen. How is it for automotive? I mean, such a developed field. And,
yeah, no, I mean, I think as I also mentioned in the beginning, that many automotive industries, they have been early in adopting, for example, Modelica and other tools for doing model-based engineering, and use that as a basis for both the design of the vehicle, but also for simulations and evaluating different control systems. So I think really that the vehicle modeling and vehicle system simulations have been adopted to a large extent by automotive industry. Yeah.
If I may add, I think the automotive industry is way ahead of the process industry in terms of modeling and uses like this, for example.
Yeah. Yeah, I agree.
You know, Toyota was the first one who bought Modelica from Hilding, for example.
Yeah.
And then it spread like wildfire.
Yeah. So I mean, modeling this, I mean, everything from the motor or engine up until the vehicle motion and its interaction with the environment. I mean, it's difficult to establish such models without a structured component-based approach. Okay, but then I think we conclude this lecture, and thank you very much for attending and listening.